Welcome back. So we were discussing the canonical ensemble, and we will discuss a different type of a canonical ensemble, which is called the grand canonical ensemble, and we will show that this particular ensemble is connected to the grand partition function omega, right? So we start off with our system, which can not only exchange energy but also can exchange particle number. So the system can exchange energy and particle number. So it's a hydrostatic system, which means that you can imagine that you have n number of particles which is contained within a box of V, but that just that n is not fixed in time, it's fluctuating in time. There's a big bath surrounding this with which particles can go to and enter like this, with which the system and exchanges particles as well as energy. So let the bath have the energy EE and particle number NE, so that again, just as we had done in the canonical ensemble, we will assume that the bath plus the system acts as a microcanonical ensemble. See, in the earlier lectures, when we did the canonical ensemble, we said that look, we could derive the distribution of the probability in finding the system in the energy state E from the fundamental relation in statistical mechanics. And if you're wondering what the fundamental relation is, it's S equal to KB ln omega. This is what connects everything, right? So in this particular case, we have E plus EE is equal to the total energy E total, and N plus NE is equal to the total energy NT. So that the probability of, let's shorten the writing, probability that S has, probability that the system has energy E and particle number N and particle number N is equal to the bath having energy E total minus E and particle number N total minus, NE, N. So therefore, we will write this as rho E comma N is proportional to omega ET minus E NT minus N. And once again, we say that the bath is so huge compared to the system that we can literally replace this ET by EE and NT by NE, which is EE is the energy of the bath and NE is the particle number contained in the bath. So again, we follow the same strategy that we did, minus del omega E del E times E minus del omega E del N times N, plus higher order terms which we will ignore. So this becomes omega B 1 minus del ln omega E over del E times E minus, so this E is equal to minus del omega E del N plus higher order terms. Sorry, there is this is going to be ln omega E, because once I have changed notations here, terribly sorry for that. This has to be omega B, this has to be omega B, and this has to be also omega B. and since I've taken omega b outside, that's why the log comes in just as in the canonical case. So you have proportional to omega b. The first one I know, so E over, this omega b is S over kb, so I have E over kbt. So just as we did in the canonical case, and this becomes del S del n, n equal to ne, n over kb. And from thermodynamics, we know that this is going to be 1 minus E over kbt minus mu n over kbt, right? If I now take a log of rho e comma n, that means this is going to be ln omega b plus log of 1 minus E over kbt minus mu n over kbt. Am I right? Yeah, this sign is not right because del S del n is equal to minus mu over t. So this becomes plus. So that I will use the expansion of is approximately x, then this becomes minus E kbt plus mu n over kbt, which means ln of rho e comma n is ln of omega b minus beta e minus mu n. If I now exponentiate this, then I have log rho of en is a normalization a e to the power minus beta e minus mu n. So I have now derived the probability that the system would be in the energy state E, n, and with the particle number. The normalization, again, as usual, is given by Z in. So Q inverse, where Q is sum over all states e to the power minus beta e minus mu n. So before, the standard route now is to connect it to thermodynamics, and before we connect it to thermodynamics, the first thing that we check is that we know that even here also, since we are talking about a fluctuating energy and fluctuating particle number, therefore both of these will have a certain mean, right? And it is this mean that I want to connect to thermodynamics. So in thermodynamics, I had the internal energy U, and this I will connect it to the mean of the energy, and I had the particle number. This I am going to connect it to the average of this n, right? But are the averages meaningful, right? So for that, I want to first check the following. Average of n. Average of n is 1 over q n e to the power minus beta e minus mu n. Which means this is going to be, so if I now take del n del mu, then n e to the power minus beta e to the power beta mu n times beta n, right? Plus, sorry, I now have to take care of this as minus 1 over q square del q del mu sum over n e to the power minus beta e minus mu n. Q is sum over all states e to the power minus beta e minus mu n. So that del q del mu is sum. I'll not always write all states. It's understood that I'm summing over all state, is minus beta e to the power beta mu n beta n. So that I have this as beta times n e to the power minus e minus mu n. If I look over here, I can simplify this as 1 over q beta over q. Well, let's write it in a way: 1 over q sum over e to n square e to the power minus beta e minus mu n minus the 1 over q square I can distribute, so there is going to be a beta factor that comes from the derivative of this, and then I have 1 over q sum over n minus beta e minus mu n, and then I have this term which is sum over n e to the power minus beta mu e minus mu n. Both of these, both of these is average of n, and this you recognize is average of n square together with the q. So you have beta average of n square minus average of n whole square, which is beta times delta n square average, and this quantity is del n del mu. Good. Now one has to express the left hand side, because I understand that this represents the fluctuations, but del n del mu might not be an easily accessible quantity. So in the experiments, for example, right, I only know that my response functions are positive, but how do I know that my del n del mu is also a positive quantity? Of course, one can argue that, look, delta n square is a positive quantity, therefore del n del mu also has to be a positive quantity. Understood. But let's see. So we want to use the Gibbs-Duhem relation. So u, for a hydrostatic system, I know that u is a function of SVN, and therefore if I use the homogeneity property, then I know that this is going to be del u del s times s, del u del v times v, plus del u del s times n. Further, I also have TdS is the first law plus PdV minus mu dn. So that del u del s is Ts and del u del v is going to be minus PV, and this is del u del n is going to be plus mu n. So the differential gives you TdS plus SdT minus PdV minus VdP plus mu dn minus plus n d mu. So du cancels with TdS minus PdV plus mu dn. So you are left out with SdT minus VdP plus n d mu is equal to 0. So if you take it to the other side, you have n times d mu is equal to minus SdT plus VdP, right? So therefore d mu is minus s over n dt plus v over n dp, right? Now del mu del n, temperature held constant, volume held constant, is v over n del p del n, right? Temperature held constant, volume held constant. And del mu del v, temperature held constant, n held constant, is v over n del p del v t comma n, right? So now, once again, this del mu del n is related to del n del mu, but it's not very useful because I have a del p del n. For that, we look at the Helmholtz free energy, which gives me dF is del f del t. Well, if you are uncertain about things, you always do it as u minus ts, which is df is equal to du minus tds minus sdt, and from the first law I have du minus tds is equal to minus pdv plus mu dn. So I have minus sdt minus pdv plus mu dn. So that immediately you see that del p del n t held constant t comma v with a minus sign is going to be what? Here also you realize that t and v are being held constant. Del p del n t comma v is going to be del mu del v t comma n. So you immediately see that this quantity is v over n del mu del v t comma n with a minus sign, right? And therefore you have del mu del n t comma v as minus v over n whole square. You substitute this over here, del p del v t comma n. Let's simplify it over here itself, because this would imply that del n del mu t comma v is minus n over v whole square del v del p t comma n. I will bring out one n, and then I will manipulate this as n by v times n times minus 1 by v del p t comma n. And all of these are familiar to us. This is the number density, which is an intensive quantity. This is capital N, and this quantity is again an intensive quantity, which we know it as a compressibility. So you immediately see that my delta n square, so beta times delta n square average is n kappa t. So that delta n square, the average of the number fluctuations, is n kappa t times kb t. And therefore delta n square will go as n, because I have a n sitting over here. All the rest of them are independent of n, or does not scale. They are intensive variables now. So square root of delta n square over n will go as 1 over square root n. So in the thermodynamic limit, when I have a large enough system, my distribution of n, which is a fluctuating particle number, becomes very, very sharply big, because you see that the width of this distribution becomes vanishingly small, right? So your mean is well defined, and therefore you are in a good position to connect it to thermodynamics by saying that, look, the average of my n corresponds to the n that we did. Good. So now that we have delta n square, the square root of delta n square average over average n going as 1 over square root n. What about the energy? So the average energy is 1 over q sum over e to the power minus beta e minus mu n. So del e del beta is going to be 1 by q sum over e, one has to be careful now, minus beta e minus mu n minus e minus mu n, minus 1 over q square del q del beta sum over e to the power minus beta E minus mu n. It's once again the same laborious calculation that one has to do, but it's not very difficult to do. Let's look at del q del beta is del beta of sum e to the power minus beta E minus mu n, which is going to be sum over minus E minus mu n times e to the power E minus mu n with a minus beta in front. Right? So del E del beta is going to be 1 by q, the minus comes outside, sum over E minus mu n minus beta E minus mu n minus, and this becomes a plus, together with this minus and this minus, this becomes a plus, 1 by q square sum over e to the power minus beta E minus mu n times sum over E minus mu n e to the power minus beta E minus mu n. Let's expand this. Minus 1 over q sum over e square minus beta E minus mu n plus mu 1 over q sum over n times e to the power minus beta E minus mu n. The second term is 1 over q average of e times average of, we will remove the 1 by q square and you can distribute the 1 by q from here and 1 over q over here, so that this becomes average of e and this becomes average of e minus mu n. So that this term is average of e times average of e minus mu average of n. And therefore, the first term is average of e square plus mu average of ne plus average of e whole square minus mu average of n average of e. So that we have minus delta e square average plus mu ne minus average of n average of e. Right? We are not done yet with this. We have to take a little more steps. We want to calculate del average e del mu, and that quantity, if I look over here, is del mu of 1 over q sum over e to the power minus beta E minus mu n, which is going to be 1 over q sum over e to the power minus beta E to the power beta mu n. Now I'm taking a derivative with respect to this, therefore I should have beta n minus 1 over q square del q del mu sum over e minus beta E minus mu n. But del q del mu we have already done. Del q del mu is just del mu of sum over e to the power minus beta E minus mu n, which is going to be sum over n beta n e to the power minus beta E minus mu n. Right? So you put back this over here, again distribute the Q's, so that you have del average E, del mu is going to be this term is average of n times E, and this times this is average n average E, right? Except now I have a beta factor common in both cases, so I have to multiply this with beta, so that del E del beta, which is del E del T del T del beta, is equal to minus KB T square del E del T is going to be equal to minus delta E square plus mu over mu beta because del E del beta inverse so that KB T square del E del T is going to be delta E square minus mu over beta del E del mu. This implies we have the fluctuations in the energy is given by this quantity is your specific heat, is KB T squared times C plus mu over beta del E del mu. We will leave this calculation up to here, noting that this will scale as n because it's a derivative of temperature, the derivative of the internal energy with respect to the temperature, and E being an extensive quantity, therefore this should scale as n. And similarly, this is a derivative of the internal energy with respect to the chemical potential, and this will also scale with n. So your delta E square average scales with n, which means square root of this will scale with square root of n, and again you recover the result over average of E is equal to 1 over square root of n. So in the thermodynamic limit, your fluctuations, your distribution of the energy becomes a very sharply peaked function. Your fluctuations in that distribution decay as 1 over square root n. And as you go to larger and larger system size, you will see that the width of this distribution becoming narrow and narrow, so that you can immediately relate the average of the quantity to the internal energy that we did in the thermodynamics and average of n with n.